Hi, this is Josh Mazur, and I'm presenting my final project iPy Notebook demo video. Um, so this whole file with its outputs is available in the GitHub repository, but I will step through every single one of the individual iPy Notebook files within this one file to demo what the project does. So this first file is create directed mask. What it's composed of is, so in order to create the masks to be uploaded to DALL-E along with the original image and a prompt, you have to create a PNG alpha mask within the image. So that essentially there's a blank portion within the image that DALL-E is going to fill in. So um, the first step is to go through, give an actual image path, the output image path, and then a XY position, as well as width and height for that alpha mask. So um, an image and its output path with those positions can be passed so that you can create a mask wherever you'd like throughout the image. This was used somewhat rarely, the idea of the project being that you could use a randomly generated mask so that you would be able to save the time of not having to edit every single image, because that would be time consuming and counterproductive to the idea behind this project. So we'll scroll down to the next one, and this is what I was just alluding to. There's also a create random transparency mask function, and that lives within the create random mask IPy notebook file. So what happens in this path or in this function, you point towards a path in and the path out. In this case, in the directories, we were just pointing towards raw images, and then we were telling it, hey, save all the images to a masked folder. But we loop through all files in the raw folder, and we pass a name so that you get the same name for input or for the raw and for the mask. But essentially, all that's happening is the same exact task. We're creating a PNG alpha mask within an image. This time given the input path and the output path of the file. We then have a min and a max size. It was pretty apparent given the data set that if you went under a certain size that DALL-E would fail to generate a stop sign a lot of times, or if you went over, it just didn't make sense contextually to have a really big stop sign within the field of view of a Google Street View car that was driving by. So yet again, just placing or same logic, placing an alpha mask within an image that would iterate through a folder and then generate your output masks. So jumping down to the next file, we have upload images for DALL-E edit of detection. So for the stop sign detection project, this would actually allow you to upload the masked image and the original image, as well as a prompt to get DALL-E to generate an image for you. So really to jump through that, all you have to do for the actual DALL-E portion is pass the input image, the mask, and a prompt, and then you get a URL response. The size of the image, we set the size to, or I set the size to the original Google Street View image size, so 512 by 512. You have to use DALL-E 2 because this feature is not available in later versions of DALL-E. So after we'd actually, create that or pass that data, we get a response that was a URL, and we would download images from that URL to the machine. And then the looping, or the way that this would go, we would point towards those raw images without the mask, the masked images, and then there was also a download path that was set up. Essentially, this portion is just getting all the PNG files within a path, finding the masked ones, and then creating the output image name based on the input image names. Here there's also a random, to create some variation, a prompt or an array of prompts that could be passed, and then we'd randomly select one of the prompts, and then we would loop through the process of, requesting DALL-E to generate that image and provide a URL, and then download that URL. So here's that going through and operating successfully. So after that, a lot simpler. The next file, upload images for DALL-E edit classification. So now we're moving on to the flower classification project. A lot more simpler. We can use DALL-E 3, and all you have to do is pass a prompt since it's completely generating the image. 1024 by 1024 is the lowest resolution that can be selected, and a lot of the original data sets for flowers were already below that resolution, so that was why the 1024 by 1024 was selected. All we would do there is select a path that it was going to save through, a path that we are going to download to. Yet again, another random or an array of prompts that we would insert the flower type we want to generate it into. We would then create a file name to dump into the path that we had selected. We would then go through with the prompt, ask DALL-E to generate the image or generate the URL or the image in the URL, and then combine the file name with, or pass the combined file name with path to download the image given the URL and the path that we are using. So here we are downloading or successfully downloading images from DALL-E 3 of the flower classification or multiple flowers. So like here, for example, we would switch between sunflower, daisy, dandelion, tulip, and rose, and just pick a number that we wanted to be generated. Okay, so from there at that point, we had all of our data sets generated. So we had our original data sets, and then based on the code that we just reviewed, we had all of the DALL-E generated data sets. So at that point, what we could do is we could take the labeled images that we had downloaded from Kaggle or that I had via Google Street View, create a data set, and then create a copy of that data set and add AI generated images. So from here on out, the iPy notebook files that are being used will either have AI images or it won't have AI images. Just basically saying which data set this belongs to. So okay, so within Collab, right here, we're just making sure GPU access is available, setting up the home or getting the working directory of Collab set up. Collab was used for just ease of GPU access. So then from here, we're installing YOLO v11 for detection models. And then we are actually getting the pre-trained pre-trained model from YOLO v11 that's pre-trained on the Cocoa dataset. So in importing all the necessary libraries there. Then here I will open up RoboFlow. Just to give an idea of RoboFlow, and we'll cover this once. So I can go to stop sign finder with AI and just show the process. Yep. So RoboFlow just makes it simple to create the data sets for training. All that you have to do is upload files for annotation, so you get them uploaded. You can then go into the actual images. Let's just pick one, and go through and add your own annotations. This process just of compiling the annotations with the image just tends to be, from my experience, quicker than using label image. Another advantage too is once you have your data set compiled, you can go to download, and get this download code, in which all you have to do is copy and paste these instructions, which we actually see here. So my API key is redacted, but you just point towards the stop sign or your project name with the data sets or your current data sets, and it composes all of that for you. So makes the process of building, like I said, all those files, annotations, pretty straightforward. So going through, getting all that downloaded is going on here. From there, we just custom train using a detection model, transfer learning from YOLO V11, and point towards the data set location with an epoch size of 50, an image size. For both classification and detection, we use the original size of the image, so 512 here. We're not going to go through all the training steps. Here you can see all the output files. We'll take a look at the confusion matrix. So with the model that has AI images, we're actually getting one of the, or one false positive in which the background is being detected as a stop sign. From there, the stop sign is being fully covered, which we'll discuss later. Here also, you can see, all of the different training, metrics as we are going through the epochs, as well. Confidence curve, recall curve as well. And then also you can go through and, run inferences on images. So here's a good example where we can see, we're detecting a stop sign, but we're also going through and picking up on the house being a stop sign. Here's another good example of, finding the stop sign. This is on a validation batch. So further examples of finding the stop sign successfully. Well, there's plenty of null images in which it's not. So just validation of the model here, and then actually at this point, we are telling the train model we're running a detection or the detection task on using the best.pt file, which is the current model file, going through all the train images. So nothing's super complex there, but we can see where we have like a no sign image, and signs are being detected with 3 signs. All the real inference and testing is done at a later step that we're about to get to. Here's a little bit more interesting, where we're actually pointing at the test data set and those images, where we could do the comparison of no sign, no detections. Here we get 1 sign and there was a sign, but yet again, we're about to get to the actual testing with output data. So this is just setting up, testing, making sure the way we're about to gather our results, the per image will be correct, and how those predictions work. But here, we actually load the model. We then get all the images within the test image data sets. We determine based on the file name if there's sign or no sign. And then from here, we're iterating through all those, running inferences, and then determining, hey, did we have a misdetection, a false positive, to be able to gather all of our metrics for the model. So just performing inferences on all of the test images. And so here we can see where we're getting past inferences, where we don't have a sign, there's no detection, then we present an image 2 when we do find. This should be another one in which the inference pass, we have 1 stop sign being detected, and that's what's in the image. And here you can see it being called out, and we iterate through that entire library of images in the test data set. So let me scroll down. Sorry, 1 moment. Up in here, and there's a good example, and it's good to just output the actual bounding box with the image to see when we fail a detection due to a false positive. So yep, and across the 100 images evaluated, there's 0 missed detections. So we had, anytime there's a stop sign is being detected, but we had 13 false positives found at a 13% positive rate. Here, this isn't necessary, just something I typically do is downloading the models to, or deploy them back to RoboFlow while downloading. We won't step through the original data set in nearly as much detail here. A lot of the steps are very similar. Setting up the directory, setting up, or getting all of the imports and libraries ready, grabbing the YOLO V11 model, grabbing our data set, given that information. We hold the epoch, image size, all parameters same for custom training, and then train the model. Moving down, exact same thing. One thing to notice, we do not have that background detection on the original model. We can see all of the training epoch steps in the data there. F1 confidence curve from training, R curve from training as well. Same thing here on a validation batch, or one of the batches used for training. Where we are showing all the positive stop signs being detected. Here we actually don't have a false detection being shown either. And then it's going through the same exact validation process as we saw before. So I'll scroll to the bottom. Let me grab this. What we'll actually see is that across 100 images, yet again, no stop signs were failed to be detected, but there were 8 positive or 8 false detections. So really, here the story, and this is discussed further within the report itself, but likely the quality, or due to the quality of the stop signs from DALI. We're probably adding a whole lot of noise to the model, and we're just overfitting to the output, or to the noise being generated from DALI. Evaluating the images, you can see lots of instances where, just like anything red that's somewhat close in shape to a stop sign gets detected. Yet again, pushing the model back to RoboFlow and downloading local files to my machine if needed. Okay, so next we'll jump into classification, or both of those models. So we first start out with the AI images added. And one thing to cover here quickly that pertains to both classification and the detection models is that on purpose, and this is covered in the report itself, but the idea is to evaluate models which don't have a lot of the training data that's necessary. This is really common in industrial machine vision when you run a bit short for a while of training images, or you might not have particular training images that you're going to need. This is really the situation which we're trying to simulate. So, normally these models, and especially if you have images available from online, or just, thousands, hundreds of thousands, millions, you're not in this case, but that's not common in certain scenarios, and we're trying to simulate and see, right, the whole purpose of DALI image generation is what images can we create to try and bridge that gap when a system is running, and then it will be gathering images and gathering anomalies or rare instances. Can we create those to get better performance in the meantime? So we'll jump back into the AI images added classification of flowers. And all the statistics there on the number of training images, test images, validation images, that is all covered in the report, and those splits are there exactly. So, This is all very similar to detection. We're going to set up our directories, working, home directory, or setting the content folder essentially in collab to home. Yet again, all the imports and installs, in this one for classification using Yellow V8. Very similar to before, installing RoboFlow, getting the workspace imported, and then from here, yet again, across the AI and non-AI data set, we're going to hold epochs to 50 and the image size to 1024. You might remember 1024 was the minimum size we could get from DALL-E 3. And then here you're doing all the training across 50 epochs. This is all a very similar story to the detection. At this point, we can see the diffusion matrix across the train type. So we're getting 3 misclassifications in the with AI model. Also, we can see here the accuracy that we get up to, rate just shy of 80%, and all the other metrics like train loss, validation loss. And then running across another validation batch, we can see the classification of tulip, dandelion, rose, sunflower, rose, sunflower, which here is actually a good misclassification example. But we're going to do that in much further detail across all images in the test data set. So the test data set is divided into 5 folders between the different classes of daisy, dandelion, rose, tulip, and sunflower. So here, here we're going through using the classification task for running prediction across just daisy. This is kind of set up or testing for doing the full evaluation on all test images. So let's scroll down to that. So here, essentially we're loading the model, and then we're creating a dictionary of all the different flower images with their different flower type. We are then iterating through in this for loop, through all those different flowers, running inferences, getting the top result with confidence, and then binning any misclassifications, running that. We scroll down to the bottom because there's 900 images to get the total detections made and then the misclassifications. Then yet again we can deploy that back, and then we do the same thing across the original data set, just then having to import a different the different model, the non-AI labeled model. Yet again, all these are being labeled within RoboFlow, as far as we have a flower classification with AI, flower classification. So that's all, yet again, the data set and the images that are available. Same training parameters used. Transfer learning from Yellow V8, epochs of 50, image size of 1024 to match DALL-E's minimum. Here we can see on the original data set quite a few more misclassifications just in the training data alone. The accuracy comes up, shy of the 80% we saw earlier. We're probably just, low 60s. And here we can already see quite a few, like this rose. These are actually tulips. This dandelion is being called a tulip. So definitely a lot more misclassifications. So here we're going to run through that same exact test on the same test data set. We load this model, we create all the or the dictionaries with the images and the flower type. We then go through, we iterate through, run inferences, get the highest scoring classification. I'll scroll to the bottom. In here we have all the the summary of those statistics for the total that were found and any misclassifications with deployment back to the RoboFlow model. and all discussions pertaining to the the results, the data, evaluating the output, those all exist within the report. Thank you for the time and attention.